Hello everyone, welcome back to this online class. Today I want us to look at how to solve partial differential equations using the method of Laplace transform. And in particular, we are given the PDE that partial u partial x plus partial u partial t is equals to x, and the boundary condition at x is equals to 0 is equals to 1. And the initial condition is that u of x0 is equals to 0. Now, this method entails 4 steps. The first step is step 1. You operate with L, where L is the Laplace transform operator on both sides of the PDE. We said L denotes the Laplace transform operator. So when you operate with L on both sides of the equation, we are going to get this. We're going to get Laplace transform of partial u partial x plus Laplace transform of partial u partial t is equals to Laplace transform of x. So remember, this is an operator in the t variables, the Laplace transform operator in the variable t, the t variable. That means we only transform the t variable. In this case, x will be a constant when you operate on it. So, what do we get when you operate on partial u, partial x? We are going to get this. So, or d dx times the Laplace transform of u of xt. I can put these curly brackets. Plus the other term, when you operate on partial u, partial t, you need to get s times Laplace transform of u of xt minus u of x0 is equals to, x is a constant, the transform of a constant. Remember, I want us to take note that the Laplace transform of 1 is equals to 1 over s. So this therefore means that the Laplace transform of x will give us x over s. So that on the right hand side we'll have x over s. Now I can say that let u bar be equal to the Laplace transform of u of x t. So with this, our equation can now be written as du bar dx plus s u bar is equals to x over s. I've left out something. Then minus u of x0 is equals to x over s. So that is step 1. Step 2, you need to apply the initial condition. Step 2, apply the initial condition. I see there denotes initial condition. Look at our initial condition from the problem. we are told u of x0 is equals to 0. So that's what we apply. U of x0 is equals to 0. So this means, the value here will be equal to 0. That one, this one will be equal to 0. So therefore, our equation can now be written as du bar dx plus s u bar is equals to x over s. This is an ODE. This is ODE of the first order. First order ODE. This equation is linear. It is linear in U bar and so you can use the D operator method. You can now use the D operator method. Let me write this in a better way. This equation is linear in the dependent variable U bar. So you can solve it in two ways. Solve it as a linear ODE or solve using the D operator method. I want to use the operator method, so we are going to say let D be derivative with respect to x. So this implies that our ODE will now become du bar plus s u bar is equals to x over s, which you can also write as d plus s u bar is equals to x over s. It is also homogeneous. This is linear in u bar, and it is homogeneous because the right hand side it is non-homogeneous, I mean, because the right hand side is not equal to 0. So this equation is non-homogeneous. A non-homogeneous ODE has two solutions: complementary function and particular integral. Let's start by finding the complementary function. The first solution is complementary function, which we are calling u bar c. How do you find it? You solve the homogeneous part, that is d plus s, operating on u bar to give us 0. So from here, our auxiliary equation is d plus s is equals to 0. So we only have one root. D is equals to negative s. This is real. This is a real root. So therefore, our u bar c is equals to a constant, call it c1, times exponential negative s x, where c1 is an arbitrary constant. Let's find the particular integral from 1 to, you write particular integral, which you're calling up bar. Here you make u the subject. Look at the equation we are solving. Let me circle it or bracket it. This is the equation we are solving. So when you make u bar the subject, we call it u bar p, subscript p. So it now becomes 1 over 1 over d plus s operating on x over s. And so this you can write as 1 over s times 1 over d plus s operating on x. X is linear polynomial of degree 1, and so I will use the Maclaurin series expansion to expand our inverse d operator. This thing can now be written as, because I want to use Maclaurin series, I can write this as 1 over s into 1 over, factor out s, we remain with d over s plus 1 operating on x. The same thing, which I can also write as, you see now in the denominator we have s appearing twice, So this can now be written as 1 over s squared times 1 over 1 plus d over s operating on x. So now expand this inverse d operator, expand this in Maclaurin's series. We are expanding when you expand, you're going to get you're going to get 1 over s squared. That expansion will give us 1 minus d over s plus d squared over s squared plus so many other terms up to infinity. This will operate on x. Remember now the d in the numerator denotes or stands for derivative. When the d is in the denominator it is differential, it is integral operator. If it is in the numerator, it is differential operator. So this will give us 1 over s squared. Take the x inside, we'll get x minus 1 over s plus 0. See, when you differentiate x with respect to x, you get 1. That's why we have 1 over s. The d squared operating on x will give us 0. That means second derivative of x, that is 0. And so higher order derivatives will be zeros. So this thing will now give us, when I open the bracket, I'll get x over s squared minus 1 over s cubed. That is our particular integral. And so therefore our general solution is always equals to the sum of the complementary function and the particular integral. What you are saying, u bar complementary, we got c1 exponential negative s x. Particular integral, we have x over s squared minus 1 over s cubed. Remember, I've used the operator method. You could also solve that equation, the one that you are solving. You could also solve it as a linear ODE by the integrating factor method. You'll get the same result that we have found here as our general solution. That is step 2. Step 3, we need to apply the boundary condition. So write step 3. Apply the boundary condition. What is the boundary condition? We are given from the problem that u of 0t is equals to 0. But you see this equation, this solution is in terms of the Laplace transform. So, and this should be 0. Let me write in a proper way. This is 0. So, we need to know what is the Laplace transform of this condition. So the Laplace transform of u of 0t, now that condition was 1. Let's see the problem. Let's see our given boundary and initial value problem. In the boundary condition, we were told it's supposed to be equal to 1, not 0, just to check. Let me check you up. Yeah, it is supposed to be 1, not 0. So I'm going to change that. I'm going to change this to 1 instead of 0. It should be 1. Now let's get the transform on both sides. That will give us the transform of 1, or simply u bar when x is 0 should give you 1 over s. That is when x is equals to 0. You see the Laplace transform of 1 is 1 over s. So let's substitute x is equals to 0 and u bar is 1 over s in our general solution. What are we going to get? We're going to get 1 over s is equals to C1. Anything raised to 0 is 1. So then minus 1 over s cubed. Remember, we are putting x is equals to 0 and u bar is equals to 1 over s. So from here it is now clear that our C1 is equals to 1 over s plus 1 over s cubed. This should be cubed, that one. So now, what is our particular solution? Particular solution is this one. U bar is equals to, now we know the value of C1, that is 1 over s plus 1 over s cubed exponential negative s x, then plus x over s minus 1 over s cubed. That's what we have. And so the last step is this one. You write step 4. In step 4, you now operate with L inverse on both sides. Operate with L inverse on both sides of equation star. This is what I'm calling equation star. So that equation will look like this. When you operate with L inverse, you'll get L inverse of U bar is equals to L inverse of 1 over s plus 1 over s cubed exponential negative sx plus x over s minus 1 over s cubed. So what is L inverse of U bar? Remember, U bar was the Laplace transform. U bar was the transform. So when you go to the function, the L inverse will take you back to the original function. That will give you U of xt is equals to L inverse of 1 over S plus 1 over S cubed times exponential negative Sx plus L inverse of x over S minus L inverse of 1 over S cubed. Let us call this equation star star. So let me work it out term by term. I will start with the term that is easy to find its inverse transform. L inverse of x over S can be written as, because x is a constant, you factor that out, then times L inverse of 1 over S. What gave us? What did we transform to get 1 over S? It was 1. So this can be written as x times 1, which you can write that as x. Let me check something here. The correction. This was x over S squared. So I left out something. That's a square. It's a square there. Even here it's supposed to be square. Supposed to be square. I left out something. So it means I'll rewrite this. I'll rewrite this because it's supposed to be S squared, not S. So that's a slight correction. So now we are saying that, let me use a different color. L inverse of x over S squared is the same as x outside times L inverse of 1 over S squared. We are factoring out x because it does not depend on the S. This L inverse will only operate on S, not any other variable. It will operate on S to give us T. The L was operating on T to give us S. Very important. And so what gave us 1 over S squared? That was T. So here we'll get X times T. Because when you transform T, you get 1 over S squared. So now we know this term. Let's also get the third term, L inverse of 1 over S cubed can be written as L inverse of 2 factorial over S2 plus 1 times 1 over 2 factorial. I'm just rewriting it, which you can now write as 1 over 2 factorial is a constant times L inverse of 2 factorial over S into 2 plus 1, S raised to 2 plus 1. And so the inverse of that one, remember 1 over 2 factorial is the same as 1 over 2. The inverse of 2 factorial over S raised to 2 plus 1, that is T squared. Now we know the third term. What about on the left-hand side? Let's see. No, not the left-hand side, but the right-hand side. First term on the right-hand side. I will write it. L inverse of 1 over s plus 1 over s cubed times exponential negative sx. It is the same as f of t minus a times h of t minus a, where f of t is the inverse of 1 over s plus 1 over s cubed. When you get the Laplace inverse transform of that one, that will give you f of t. And what I'm calling a, and a is equals to x. Which theorem am I using? I'm using the second shifting property of Laplace transform. Second shifting property of Laplace transform. Let me state it here. You take note of the second shifting property. Take note. What you're calling the second shifting property is that if, let me state it here, you write if the Laplace transform of f of t is equals to f of s, comma, then the Laplace transform of f of t minus a times h of t minus a should be able to give us f of s times exponential negative, that should be negative a s. This is called the second shifting property of Laplace transform, and that is what I'm using to be able to find now the inverse. Because when I take the inverse on both sides, I get f of t minus a times h of t minus a is equals to L inverse of f of s times exponential negative a s. So I was comparing this one. Let me bracket it. So when you do the comparison, look at what we have here. It is clear that when I compare the exponential negative as, and here we have exponential negative sx, it means our a is equals to x. And our f of s is 1 over s plus 1 over s cubed. So let's now get f of t. We can now be able to find f of t. Look at this. Let me write with a different color. If you look at this one, L inverse of 1 over s, that is 1. And the inverse of 1 over s cubed, we have just found that to be 1 over 2 t squared. I didn't explain what we mean by h of t minus a. That function is called the Heaviside function, or a unit step function. This is how it is defined. I'll also write it here. The function h of t minus a. It is defined in this manner. Let me write. Also, I want us to take note that this function h of t minus a is called the Heaviside function. And this function is 0 whenever t is less than a. And it is 1 whenever t is greater than a. If I were to sketch it, this is the function. This is x-axis. But now instead of x-axis, we have the t-axis. So instead of x, I'll write t. And on the y-axis, we have h. So that if I have 1 here, and I have a here, at point A, the function is discontinuous. So it is 1 to the right of A, and it is 0 to the left of A. That is the function h of t minus A. We are calling it a unit step function or a Heaviside function. Now, back to our inverse transform. We are saying A is equals to x. So now, therefore, you can now say therefore, I'm working out this. I'm working out this. I know f of t to be 1 plus half t squared. So, based on that one, we can now be able to get f of t minus a. F of t minus a is the same as f of t minus x, because our a is x. So, when you replace where there is t, you put t minus x, we are going to get 1 plus half t minus x, and that is supposed to be squared. We also need to know what is h of t minus a. T minus a, our a is x, so that is h of t, I'll write it, h of t minus x. You see, in this case, I don't know h explicitly, but I know it is piecewise. It is 0 to the left of a, and it is 1 to the right of a. You see, this Heaviside function behaves like a switch. That switch is off until t is equals to a, at which point it turns on. So it simply behaves like a switch. So therefore, we can now say that the inverse transform of 1 over s plus 1 over s cubed, that in bracket then times exponential negative sx, should now give us the product of f of t minus a and h of t minus a, which we have found. So we multiply the two. So you can just say therefore, let me write it. Remember, I'm going to multiply the two to get our solution. So when it comes to Laplace transform, we just need to master the 4 steps. I'm going to complete that. Just remember the 4 steps. They're very simple. I'm going to complete it. The first step, you operate with L on both sides. The second step, So we are saying that now L inverse of now we had 1 over S plus 1 over S cubed times exponential negative Sx will now be the product of what we got here and this. So that can now be written as 1 plus t minus x is supposed to be squared divided by 2 times h of t minus x. And so going back to our particular solution, let me take you up. Our particular solution, which was equation star, I now know the inverse transforms on the right hand side. We just replace, and so that will be our particular solution. So let's substitute what we have found into equation star. So I can just write here that upon substitution, our equation star will now become, when we substitute, we are going to get u on the left hand side, u of xt. On the right hand side, we are going to get 1 plus t minus x. This is supposed to be squared. You divide by 2. Then we multiply this by the heaviside function of t minus x plus we got the other one. What did we get? Let's check. In the other one, let me take you up. Second term, what did we get? We got x times t. That is the second term. I can take it, x times t. I'm going to write x times t in the second term. The other term we got 1 over 2 t squared. So minus, because it was negative. So that we'll have xt minus half t squared, or simply t squared over 2. So here we'll write plus xt minus half t squared. So this is our particular solution. So thank you all for watching. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech and you'll find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at other problems involving Laplace transform. Bye-bye.